like, I'll wait for a minute. And CV is 5 pounds R, and then delta T. Delta T. Should get like 15.2 times 10 to the 10. Just copy those. 6.08 times 10 to the 5th. 21.3 times 10 to the 5th. So let's look from 1 to 2. Heat entered or left the system from 1 to 2?
Left.
Entered. Positive. Yeah, entered. 21.3 times 10 to the 5th. Joules has entered the system. Okay. Let's do from 2 to 3, and then the other ones I will just write down the answers. 41 minutes. So from 2 to 3, it's isochloric. From 2 to 3, it's isochloric, so W is 0. Since W is 0, then the change in thermal energy is simply equal to Q, and both of the, and we get MC is W. So N 40.63, 5 halves R, and then delta E from 2 to 3, so 900 minus 27. So multiply. With minus 15.2 times 10 to the 5th. Minus 15 on 2 times 10 to the 5th minus 15 on 2 times 10 to the 5th. Okay. So here, heat left. This many have left. And then we have to do 3 to 4 and then 4 to 2. Yeah,
The total thermal energy change to be 0, I think.
in total, yeah. Should be, here,
Yeah.
so next we will do, what you will do. I will just write down the answers. For 2 to 3, I'm sorry, for 3 to 4 and 4 to 1. Just repeat. You just have to put different temperatures. So I will write down. For this one, minus 2.03 times 10 to the 5th for the work time. The heat is minus 7.08 times 10 to the 5th. And then for the thermal energy, minus 5.06 times 10 to the 5th. Yeah. So from 2 to 3, more heat gets out. total work, just add these, and you should get 4.05. So 0.05 times 10 to the fifth. So what can we say? Well, we can say the total work is what I just wrote, 4.05 times 10 to the fifth joules. How about QH? What's the heat that has entered the system in this cycle? What's the heat that enters the system? So we will be adding these, right? All the heat that has entered. Right? So you're saying 26.36. So I would just I've added it. 26.4. 26.4 times 10 to the fifth. And then how about QC? How much heat left the system? Just add them. The ones that left. The ones that left, you got 15 and 7, that's 22.28. 22.3? About 22.3 joules left, times 10 to the fifth left. So just count them. These two entered and these two left. Next you find your efficiency, because we did this, so we need the efficiency. Efficiency is easy when you have everything. You can do it this way. It's 4.05 times 10 to the fifth over 26.4 times 10 to the fifth. This is cancelled. It's about 15%.
So what is that ending?
Okay. I want to discuss refrigerators and air conditioners now. So these clockwise cycles are heated. If counterclockwise, it would be refrigerators. Counterclockwise, we would be running in reverse. So instead of doing work, it would be work done on it. So meaning total work would just be a negative number. The engine would be negative, not the engine, the refrigerator would be negative. Work done. Okay. So can I erase these boards so that I can discuss the next one?
Yes.
Okay.
More pollination. Tapi nggak begitu gede karena nggak ada heat change.
A lot greater?
No, really?
Yeah, usually, you can efficiency is good, like 15, 20%, 30%. No, we didn't do refrigerators.
Soalnya kalau
We'll discuss it.
Yang kita work di sini tuh work by. Jadi E thermal 0 sama dengan minus work by-nya, which is minus 24. Go for the first one. No. Minus with minus. Minus minus.
Tuesday we have.
Hindi mo sana tayo mo na
Because the thermodynamics was out.
Alright, refrigerators and air conditioners. We know heat flows from higher temperature to lower temperature. But a refrigerator or an air conditioner in this room, it makes heat flow from low temperature to high temperature. Outside is hotter, but it removes heat from this room and throws heat to the outside. That's how it removes it. But it doesn't happen by itself. It does not happen spontaneously. Work must be done to make it happen. So, how does the schematic look like in that case? This. We still have QH and QC and W. So here's how it looks. Our room is here, and it will look like this. Work must be done in order to remove heat from the cold place. This is our room. In order to cool our room more and more, work must be done. And conservation of energy says the heat that we throw into the outside, that we add into the outside, will be QH. This is the cooler place. This is the hotter place. The cold reservoir will be our room, and then the hot reservoir will be the outside. Yeah. And then the work done, who does the work? It's the electric power. Somebody consume electricity. So work is done on the system. So you see, it's like this one, but it runs in reverse. So instead of being clockwise, that cycle will now be counterclockwise. So what do we care about if we want to define something called the coefficient? In that context, it's not the. In this case, it's called the thermal efficiency. In this one, it's called the coefficient of performance. So let's define coefficient of performance. There are two different ones actually that you can define. It's about what you care about. So for example, for an air conditioner or an AC air conditioner or a refrigerator, K, which is the coefficient of performance, is defined as follows. Similar to this, what you get versus what you pay. What do you get? What do we get in this room from what does the air conditioner do for us? It removes heat. So what we get is the heat that's removed. What do we need? What did we have to pay? Work. That's the coefficient of performance for an air conditioner or a refrigerator. Yes. Yes. Work done on the work done on the system would be positive. Yes. Yeah. Work done by the system would be what? Negative. So it's a counterclockwise. Yeah. So now there is something called the heat pump. The heat pump is, so let's think about an air conditioner first. An air conditioner, you have, let's say you put an air conditioner in this room, it will remove heat from this room and throws it to the outside. So you have an exhaust that you throw outside, right? That pumps air, that pumps hot air into the outside, right? That's the exhaust. So you live in this room, you live here. This one you're removing heat from. A heat pump is the same air conditioner, but you live here. want to heat your room. You live here. So what you do is, suppose you reverse the air conditioner. The exhaust is into the room, and then it pumps cold air to the outside. So the hot air comes to the room. So what you care about for a heat pump is the heat that enters into your room in comparison to the work that was done. Yes?
So could you put a refrigerator next to the engine, like where QH enters is where QH leaves? Like, could you just, like a Lego? Right?
Let me see. Oh, combine them together? Feed one into the other?
Yeah.
Yeah, you could, but it's not gonna be 100%. We can discuss that afterward. Yeah, yeah. I see what you mean, yeah. Let's worry about that maybe next time. Yeah. Okay. Good question. Yeah. I see. At first I didn't understand. Yeah, I get it. So the coefficient of performance for a heat pump, I think you have an example in homework 3 or 2, probably homework 3, or maybe 4, I forget. One of them, it has a heat pump, and the coefficient of performance for a heat pump is QH over W. In that case, for a heat pump, so this is for a refrigerator and AC. For a heat pump, it's defined differently because you care about the heat that you get. Because you live here. For a heat pump. For an air conditioner, you live here. I thought it was a hand. No? Okay. So I have a question for you. It's a conceptual question that gets asked, and let's see if we can answer. Have you seen those portable ACs or like window ACs?
Yeah.
You want to, let's say you don't have time, you want to cool your room, it's hot, you plug it, and you just set it on your table, on your counter. And the hot air gets pumped into your room, and the cold air also gets pumped into your room. Okay, so both, you're getting both. So, and the question is, will the room get cooler, warmer, or maybe stay the same because you're pumping cold air and then you're pumping hot air and then
Cooler.
hotter?
Cooler.
Cooler?
Cold but lower the pressure.
But overall,
Colder.
QH is bigger.
Cooler.
Jack?
Okay, so if it's perfectly efficient, then it will stay the same. But if it's not perfectly efficient, then it'll get warmer.
What does perfectly efficient mean?
Like if the refrigeration is operating at
With no work?
if it's
Okay.
It's all work. Like it's
So this is, so somehow you don't do any work and then it pumps cold air. Right? So the second law, we say that's impossible, but we'll get to that. Yes? Huh? You tried that, and it gets hot, right? Yeah. Yeah. So it actually gets hotter. Here is the reason. Like you said, QH is bigger. So here's what happens is, let's say you remove 10 joules of heat. And let's say in order to remove from the room 10 joules of heat, you consume or you have to do 3 joules of work. Right? Just for the sake of argument. So 10 joules of heat removed, it cools it down by 10 joules, and it has to do 3 joules of work. But then what does it exhaust into your room? 13 joules. So it's a net of 3 joules, right? But if it were, like you said, somehow you can just, it runs on its own, then it will stay constant, right? That would be nice, right? By the way, what would be the coefficient of performance if Jack said, if W it requires very little work, if W is almost 0 and it still removes heat, it's so efficient. What would the coefficient be? It will approach what? It will approach infinity because this one is some number, some finite number. This one is approaching 0. So the coefficient of performance would approach infinity. That's not possible for it to be just with no work and then somehow the cooler room gets cooler. Actually, if you think about it, that's not nice, that's not good. If every time you put two things, one of them cooler than the other, the cooler one just freezes and the other one just boils. So imagine you're the cooler person next to a hotter room. What happens? You freeze, and then the room gets really hot, and then, you know, then the end. So that's not good, right? So it's the way things work right now is good, right? All right, so let us do an example of this. Do an example on a refrigerator, okay? So consider, suppose you have, let's say a refrigerator with K equal to 5. So this is a refrigerator with a coefficient of performance equal to 5. Okay? And the refrigerator gives a power input, or it is consuming power in order to cool. It's consuming 500 joules every second. It consumes 500 joules per second. So that's the power needed to run the refrigerator. Yes. Yes.
Is K a percentage just like a zero?
K is, in this case, well, it would be 500%.
So is it like 0.05 and using calculations?
No, it's actually just 5, the number 5. Meaning, you do 1 joule of work and you can remove 5 joules of heat. Yeah. So for a refrigerator, K is typically more than 1. For heat engines, it's less than 1. Yeah. So that's K, and it consumes 500 joules. So the work done done on the refrigerator is 500 joules every second. Okay. So here's the question: suppose you put 500 grams of water, or half kilogram. So here is water. I have 0.5 kilograms of it. Let me make this bigger. So 0.5 kilograms at 20 degrees Celsius. Okay? So you put water in the freezer, and you want to freeze the water. So you would like to turn it into ice at 0 degrees Celsius, right? We're assuming everything's perfect. How much time will it take? Find the time. So find the time it will take to freeze half kilogram of water at 20 degrees Celsius and turn it into ice at 0 degrees. So what needs to happen is water at 20 needs to become water at 0, and then water at 0 needs to become ice at 0. And so the question is, how much time will it take? So what we need to do first is figure out how much heat needs to be removed, right? How much heat, because we have to remove heat from it in order to freeze it. And then that heat removed is our QC. And knowing QC, and knowing the coefficient of performance, we know W. And then knowing W, we know how much time it will take to freeze it. So let's take it in steps. How would work it? So I have water at 0 degrees, and it's half a kilogram of it. I need to turn it into water at, I'm sorry, it's at 20 degrees at first. Water at 0 degrees, and then make it into ice at 0 degrees. Okay? And the mass is 0.5 kilograms. Okay? So this is calorimetry. So we need to figure out how much heat is removed, and that would be our QC. So, all right, so what do we do? NCV delta T, NCP delta T, or MC delta T?
MC delta T.
This is liquids and solids, yes, it's MC. CW, right? Times delta T. That's for this step, right? From here to here. How about during the freezing process? The temperature is not changing. Yeah, the mass times the latent heat of fusion, plus or minus? Plus, so I need to add heat to freezing?
No,
Minus.
minus.
Yeah, I need to remove heat from freezing. Yeah. Remember there was that plus minus? If you're turning ice into water, you have to add heat, that's plus. But here we're going water to ice, we need to remove heat, that's minus. Okay? So let's do this part. So 0.5. We need to look up the this thing here, specific heat for water. It's 4,190. So in a Quizlet test, it's given to you, but here is the example, so we know the numbers. The delta T, it started at 20, ended at 0, so 0 minus 20, so that's going to be 8. But we're removing here. And then 0.5. Latent heat of fusion is 3.33 times 10 to the 5th joules per kilogram. So we get our Q. This is the add these. Yeah. Yeah. So 0 minus 20 will be negative. Yeah. Yeah. This one we have to add because there is no temperature here. So do I have? So I get minus 2.084 times 10 to the 5th joules. That many joules of heat. So QC is what? We have removed heat, so what's QC? Yeah, it's this, but with just positive. That's the heat removal, 2.084 times 10 to the 5th joules. That's the heat that was removed. So how much work must have been done in order to remove this much heat? How much work was done?
Using the K is equals to QC over T.
Yeah, so in order to find the work done, use the definition of this coefficient of performance. The coefficient of performance is QC over W. So W would be QC over K. And so 2.084 times 10 to the 5th over 5. That's what, 41,680 joules of work. So now, how much time will it take to remove this much? I mean, to do this much work? How much time will it take?
Divided by 500.
Yeah, so it's consuming 500 joules per second of electricity per second, right? So if you wait 1 second, it will remove 500 joules, or it will do 500 joules of work. If you wait 10 seconds, it would be 5,000. 80 seconds, it would be 40,000. So slightly more than 80 seconds. So the way we can do it, we can say power. Work over time times the time will be work over the power. The work is 4,180 over 500 joules per second, so that's over 80 seconds. So about 83 seconds. Do you think that's reasonable?
Like, what's the average coefficient of performance for refrigerator?
I believe that's 5 is a reasonable number.
Oh,
Yeah. to free to water. Do you think that's reasonable? That's really fast, yeah. Can you see why that? Yeah, who said there's there? Yes, yeah. This is saying all the power of your refrigerator is just trying to go to this single piece of water. But there is other stuff in the refrigerator, including air. So, yeah. Yeah, and just have that, the water, and then there's just nothing but that. Okay, so typically it takes 10 minutes, 15 minutes, I forget.
10.
Something, yeah, some number. Yes,
Would it work in a vacuum?
the refrigerator? Inside it? Well, it would collapse probably. Yeah, there's pressure from outside, yeah.
If it was a really strong refrigerator, would it work if there wasn't any air inside? And
I suppose.
What if it was a refrigerator in a vacuum that had a vacuum inside?
There would be nothing to collide.
You
Yeah.
can,
how
that would be an
the-
engineering problem, I guess.
Yeah.
My
Let's make one.
answer would be, ask an engineer. Okay? Let's go to, we're going to go to the Carnot cycle, but I have 9 minutes, but I need about 20 to complete it. Yeah.
I'm sorry, Professor?
Yes.
On the part where we're calculating MCW delta T, if you're removing it from the system,
Yeah.
wouldn't it be negative also?
Yeah, this is negative.
The first one is the.
Yeah, this is negative. 0 minus 20 would be a negative number.
Oh, that's right.
We don't include the negative before that in the equation?
The negative, for this one, no. The negative, the temperature change is negative, so it would be negative anyway. But for this one, when you see it listed, it always says plus or minus MLF. And then you have to decide whether to use the plus or the minus, only for this one. This one is already decided for you.
Oh, okay.
Yeah. So the Carnot engine,
By saying you have to decide because you have to add plus or minus for
yeah. So if water is freezing, it means heat was removed.
Yeah.
So you have to use the minus sign. If ice was melting, then heat was added, so you have to add with a plus sign. Yeah. Okay. Let's see here. I have the Carnot cycle, and then we will, right after that, we will talk about the second law of thermodynamics. And I think I will have about 30 minutes on Tuesday, and then we just need probably less than an hour on Thursday. So chances are next week we will start electricity. That's good, yeah. That's good. Yes.
Where does the QC come from?
The what?
The QC.
So that's the heat that was removed.
No, like if we want to talk in AC, like the fan is working to for QC.
Yes.
So it's like only the opposite of the Q heat.
So this is the heat that was removed, and when you say QC, it's understood that this is negative. This is heat. We had to remove this many joules. So this is QC.
Like how to make QC? How to make QC? How to make QC?
I'm not sure what, how do you remove the heat?
Yeah.
How do you remove heat?
Yeah.
By putting it in contact with something that's cooler.
Somewhat?
Something that's cooler. So let's say I have a hot object, I put it next to a cool object. So heat will flow from the hot object to the cool object. So when the heat gets removed from hot to cold, that's QC.
So with the help of Freon, with the help of what? Freon. Freon.
Yeah, there would be something that's cooler, yeah.
Also, there's a Freon on it that makes it cooler.
Well, that's inside the refrigerator. It gets in the construction of it. Just